from 0 to 5 seconds. So the maximum value of this would obviously be at t equals to 5 seconds, because this is a quadratic, 8t square increasing function. So we have maximum value at t equals to 5 seconds, which is 8 into 25, that is 200 amperes. The second question is to calculate the RMS value of this current. So you have the RMS value as root mean square. So you basically take the square, the average of squares, and then you take a square root of that. So we have 8t square whole square, integration of that by 5 and root of that. So it's, you just have to calculate this, and from 0 to 5 seconds, and you will get 89.443, and the answer is given as 89.5 amperes. So it's fairly equivalent. The third part is the energy stored during this period. So we know that the energy stored in an inductor at a particular instant is the half of Li square. L is the inductance, and I is the instantaneous current in the inductor. So then, since we are asked that the energy finally stored is asked, we'll report the energy as half into 0.25 into I squared. That is 200 squared. We'll get that as 5000 joules.
Sir,
Yes.
sir, in this, if we consider the energy stored, why did we take the final current?
It should be mentioned. I got it out. It should be mentioned that the energy stored fine at the end of the period, because it's a little arbitrary. So I'll change this in the tutorial if
Oh,
required.
okay, sir.
Uh, for Are there any other doubts? Right. So moving on. This one is a fairly straightforward question. Two coils connected in parallel, voltage of 200 volts is applied to the terminals. The total current is 25 amperes, and the power dissipated in one of the coils is 1500 watts. So what is the resistance of each coil? So assuming that the 1500 watt resistance is R1 and the other one is R2, without loss of generality, obviously. We have the power through R1 is 1500 watts, and voltage across both the resistors at 200 volts. So 200 square V square by R is the real power across the resistor. That would be 200 square upon R1 equals to 1500. We get R1 as 26.67 ohms. And for finding R2, we have another equation or another value which we can compare. That is the total current, which is equal to 25 amperes. So the total current would be the sum of currents going through R1 and R2. So the current going through R1 would be 200 voltage by R1 and 200 by R2, sum of both of them, and that would be I, which would this would give us 25 equal to 200 by R1 plus 200 by R2. We know R1, plugging in the values, we get R2 as 11.48 ohms. Any doubts? If there are no doubts, we'll move on.
No, sir.
Okay. So for the fifth question, resistance R is connected in series with a parallel circuit comprising of two resistances of 12 ohms and 8 ohms respectively. The total power is 70 watts when the applied voltage is 20 volts. So the circuit looks something like this. Two resistances, 8 ohms and 12 ohms, they're in parallel, and we have another series resistance, capital R, unknown, and the total voltage across all of them is 20 volts. So what we need to do is find capital R, for which the total power dissipated in the circuit is 70 watts. So we try to find the R effective of this circuit, which would be R plus 8 parallel 12, which would be 8 into 12 by 8 plus 12. and that comes out to be 4.8 volts. So the effective R across the 20 volt voltage source is R plus 4.8 ohms, and the total power dissipated would be 20 the voltage square upon R effective, which would be equal to 70 watts. So we get 20 square 400 by 70 is equal to R effective. R effective comes out to be total of 5.714 ohms, and from here we can see that we subtract the 8 parallel 12 known resistances. So 5.714 minus 4.8 is 0.914, and the answer is given as 0.91 ohms. Okay. So for the next question, we have a wire. This is related to magnetic fields. Till now, we're, I think, doing questions on current and electric fields. This question, so you must have done this as well during your JE time, but we'll do this anyways. A wire is bent into a plane square of 12-inch side, and the current of 250 amperes is circulated around it. What is the magnetic flux density at the center of the square? So you know that if we treat each of the four wires as different components, and each of the magnetic field for each of the four wires is different, and add them all, you know that by the right hand thumb rule, the magnetic field at the center of the square would be out of the page, right? And you can add all of them, take all of them separately and add all of them. So for so this is the formula that you might have studied. The for a particular line, and sine theta 1, sine theta 2, theta 1 and theta 2 are two angles that are subtended by the non-infinite line. So if you plug in the value of here, we would have sine theta 1. Theta 1 has 45 degrees and theta 2 also has 45 degrees because it's symmetric, and the total sum is 90 degrees. So for a single wire, we would have point mu naught I by 4 pi a. A is the distance, into sine theta 1 plus sine theta 2, which would be 1 by root 2 plus 1 by root 2. And 4 times that, you would get this expression, 2 root 2 mu naught I by pi a, and which would give you the desired answer, 0.927 millivapor per meter square. You can try it yourself. If you face any doubts, you can ask me after. You can put it on the chat window or anything. So the seventh question. Moving. So yeah, does anybody have any doubts till now?
No, sir.
Right.
No, sir.
Right. Okay. So the next question is about uh, voltmeters and having resistances. Two voltmeters A and B having resistances 5,000 ohms and 15,000 ohms respectively are joined in series across 240 volts. What is the reading of each voltmeter? So these are, so you must have studied about voltmeters, and so you mostly must have focused on ideal voltmeters which have infinite resistances. You must know the fact that you can't connect two ideal voltmeters in series because they have infinite resistance, and they can't. The KCL and KVL don't add up. You'll probably learn this, or you might have learned this already. But these are non-ideal voltmeters, and the voltages would obviously be divided on the basis of in the ratios of their resistances for non-ideal voltmeters. So here we have a 240 volt voltage source and 5,000 ohms and 15,000 ohms voltmeters. The total current would be 240 upon 15,000 plus 5,000, and the voltage across V1 would be this current into 5,000 ohms. That would be 240 by 4 into 1, because that is the ratio of the resistances, 5 by 15 plus 5. So it would be 60 volts. So 1 by 4, and the other would be 3 by 4. That would be 180 volts. Just let me know if you have any doubts in this. Right. So moving on. We have the eighth question. An air condenser consisting of two parallel square plates of side 50 centimeters is charged to a potential difference of 250 volts. When the plates are 1 mm apart, find the work done in separating the plates from 1 mm to 3 mm and assume perfect insulation. So, given that we have perfect insulation, we can say that when these plates are charged at 250 volts, there's a certain charge that gets accumulated on the plates, and because of the perfect insulation, the charge would remain constant. So we first find the charge. The initial charge would be equal to the final charge, and we first find the initial charge Qi, that would be C into V, and that comes out to be 553.386 nanocoulomb. And now we have to find the work done. We can find it in two ways. We can find it in the a way that we just take the delta of the energy change, and energy change can be written as v square by 2c, half cv square, or q square by 2c. But over here v would change, but q would not change, so we would prefer that we take half of q square by 2c. Otherwise we'll just q square by 2c. Otherwise, we'll just have to take the updated voltage, and that would be more of a hassle. This is easier. So we take half into q square by c, and the difference of these, we'll get the total energy change, and that would be equal to the work done. Ninth question is resistance. So is that clear till now? Eight questions.
Yes, sir.
Okay.
Yes, sir.
So ninth question is a resistance of 10 ohms is connected in series with two resistances, each of 15 ohm, arranged in parallel. What resistance must be shunted across the parallel combination so that the total current should be 1.5 amperes? Right. So the total resistance. So we find the total resistance if because we're given the voltage and the current. We have the total resistance required according to the question to be 13.333 ohms, and we have 10 ohms connected in series with two resistance of 15 ohms. So the two resistance 15 ohms parallel would be 7.5. We need to find a resistance which is shunted across this parallel combination, that is shunted with 7.5 and with series with 10, that is equal to 13.333. So from here we get this value, that is the three resistances in parallel. Two are 15 and one is unknown. It should be equal to 3.333. When you get this minus 10, and you can solve it, and you'll easily get the required resistance to be 6 ohms. It's not very difficult. So for the 10th question, this is also a fairly straightforward question. You just have to look out for the currents and voltages. So I'll explain the question first. A constant voltage E is applied to n groups of rheostats in series, where each group has m identical rheostats in parallel. So basically, you have resistances, rheostats, n groups of them, and these are connected in series, and each single group has m resistances in parallel. So you have m parallel resistances, series with m parallel resistances n times, and you basically find the current across this whole circuit and then divide by m. That would be the resistance through the current through one of the resistances of one of the groups. So that is what is given before in the before part, and the next clause is one rheostat burns out in one group. So one of the resistances out of the whole setup burns out. This would change the total current. This would change the total resistance of the group, and hence the total resistance of the circuit, and hence the current of the circuit, and the current in the circuit across one resistance. And here you have to find the percentage increase in current in each rheostat of the faulty group. So when you take the total current, you find the total current and divide by m minus 1 and not m, because it's given for the faulty group and one of the rheostat burns out. And it's an open circuit and current cannot pass through it. So you will easily get the answer. It's not an issue. If you have any doubts, you can ping me on the chat. You got the question. You got what the question is asking, right? That is important. You will get the answer eventually. Is the question clear to everybody, or do you have any doubts?
No, sir, it's clear.
Right. So you must have done so. So we have another question for non-ideal voltage sources. Yeah. So we have a question of non-ideal voltage sources which have an EMF and an internal resistance. So this question says a cell supplies 48.8 milliamperes to a 25 ohm load and 25.9 amperes to a 50 kilo ohm load. So there has to be an internal resistance for these two to be true. Otherwise, the things won't add up. Determine its EMF and internal resistance. So you basically have two equations and two variables. That would be the EMF, the current, total current you're given, and the total resistance you have. So suppose the internal resistance is small r. So the EMF would be equal to the total current into R plus 25 for the first case, and the current into R plus 50 kilo ohm for the second case. And I think there's a typo here. There might be, there might not be. I'm not sure because it's given 50 kilo ohm and 25 ohm. I'll just confirm it. I'm not sure about this, but yeah, I'll confirm it and update the tutorial. But it's a very straightforward question. You'll have two equations, two variables, R and E, and you'll solve for them and you'll get the desired values. For the next question, for the next part, we have find the terminal voltage for the 11th question only. We have find the terminal voltage of the cell when connected to a 40 ohms load. So this is again fairly straightforward. You have the total current to be the EMF upon small r, that is the internal resistance, plus 40, and this would be the total resistance. We have the current. We just need to subtract the EMF across the voltage across the small r, that is the internal resistance, and subtract it from the EMF. We'll get the answer, and that would be E minus I into R, the total current, and you will get 1.275 volts. Not very difficult. Let me know if you have any doubts. It's not an issue. This is the first tute. You'll have to have your basics strong. If you have any doubts, you just ask me during the tute, or you can just message on the Teams chat. I know I'm going a little fast, but these you have covered these concepts a long time back. So stop me if you have anything to say. Okay, so for the 12th question, 20 volt battery with an internal resistance of 5 ohms is connected to a resistor of X ohms. If an additional 6 ohm resistance is connected across the battery, find the value of X so that the external power supplied by the battery remains same. So the confusion that this can created was what is the external power? The external power would be all of the energy lost or energy supplied to the resistance except the 5 ohms one, because that is an internal resistance. So you calculate the total current, you put the energy lost or energy supplied as I square R, and R would be the external resistance. So for the first case, you have I is equal to 20 by 5 plus X, and the external resistance as X. So the power would be I square into X. The second case would be the net current would be 20 upon 5 plus 6 plus X. That is 11 plus X. This would be I dash, the new current, because we add a 6 ohm resistance. We have I square into 6 plus X. That is the new updated external resistance. We equate both of these, and you'll get a quadratic, and I guess you'll get the answer is 2.83 ohms, and which matches the answer in the tube sheet. Yeah, I think you just have to equate both the powers and you'll get the answer. So the next question is, we have two voltage sources with internal resistances, and they both supply power to a single resistance, which is of 1 ohm. Two 12-volt batteries with internal resistances 0.2 and 0.25 ohms respectively are joined in parallel, and a resistance of 1 ohm is placed across the terminals. So both these resistors supply energy to the 1 ohm battery.
Sir?
1 ohm yes.
So in the previous question, could you please open that solution slide?
Yes.
I have one doubt there.
Yes.
Question number 12, sir.
12.
Solutions. Yes. So here the external power should be I square times R effective. So in the second case, it should be 11 plus X, no?
No. So 11 plus X. No. So what is happening over here is current is 20 by 11 plus X. That you understand, right?
Okay,
No issues in that.
understood, sir. Okay, sir.
Yeah.
Understood.
That is the external resistance. So you just have to see the external power. The other power would be internal, and it would just dissipate in the battery, and the battery would heat up.
Okay, sir.
Okay. Any other doubt?
No, sir.
Right. Okay. So moving on. We have two 12-volt batteries, internal resistance 0.2, 0.25 ohms, parallel with supplying power to a 1 ohm resistance. Find the current supplied by each battery. So there are many ways to do this, but a simple way would be to apply KCL. So you have basically so you take, it's a little blurred. So this is basically you take two currents, I1 and I2, or you can assume currents in the loops, or you can assume currents in the branches. So let's say in the solution we have branches, so we'll take branches. This is I1, this is I2. From the first current source it's I1, from the second through the second current source it's I2, and for the 1 ohm resistance it would be I1 plus I2. And you apply KVL for the loops. Two loops, you can choose any two loops. You can choose the small loop, two small loops, or one small loop and one bigger loop. You'll have two equations in I1 and I2. You just have to solve them and you will get the answer. It shouldn't be a big deal. You get I1 as 6 amperes, the current through this branch, and I2 as 4.8 amperes, and obviously the current through the 1 ohm resistance would be the sum of both, that is 10.8 amperes. 10.8 amperes. When you solve this, if you have any doubts, just message me on Teams and I'll be happy to answer. For the 14th question, just a minute. Okay, so the 14th question, stop me if you have any doubts. For the 14th question, two heaters A and B are in parallel across a voltage supply voltage V. Heat array produces 500 kilocalories in 20 minutes and heater B produces 1000 kilocalories in 10 minutes. The resistance of A is 10 ohms. What is the resistance of B? So you know that V square by R, or the we have I square R or V square by R, whatever that is the power across a resistance, right? And here we are given the total energy. So we just have to divide it by time and we'll have the power, and we'll equate that with V square by R, because we have a parallel, so you can see the setup. We have two resistances in parallel, so we have a V constant, so we'll use V square by R for simplicity. You can also use I square R, but that would be complicating things. So we have V square by RA and V square by RB, the powers for both the resistances. The ratio of the powers would be 500 by 20. This would be the power for A, and 1000 by 10, which would be the power for B. And so this is 1:4. As you can see, 500 by 20 and 1000 by 10. The powers are in the ratio of 1:4. And you can see that V square by RA and V square by RB, this should be inversely proportional to the powers are inversely proportional to the resistances. And if A is 10 ohms, you'll get B as 2.5 ohms. It's just straightforward. You just have to equate the ratios, because that is 1:4. That so the RA is equals to 4 times RB, basically. So this part is you can just do it by ratios. You don't even need to calculate anything. For the next part, if the same heaters are connected in series across the voltage, how much heat will be produced in 5 minutes? So for this, you have to do some conversions. So you will need this 1 kilocalorie is equal to 4184 joules. Yes. So you just calculate the power V square by R effective, the new R effective. You have the 2.5 ohms and you have the 10 ohms. You just calculate the R effective. You also need to calculate the V from here. So you have V square by 10 is equal to 500 kilocalories by 20 minutes. You calculate the V, you calculate the power, and you multiply it by 5, you get the energy. This was a little involved question. You can think about it. Take 1 or 2 minutes to think about it, and then we'll move on. It's fairly straightforward, but yeah, there are a few things involving, and you haven't tried it, so I'll just stop here for 1 or 2 minutes and let you think about it. Let me know if we can continue.
Yes, sir.
Okay.
Different.
Okay.
Okay, sir.
Okay. So you'll get the final energy or energy dissipated or heat to be 100 kilocalories. It's not very difficult. The A and B are in series, and you just have to calculate the total resistance. You know the total voltage from the previous part, and multiply it by 5 into 60. That is the total time, and you'll get the answer. Moving on. 15th question. Find the equation of voltage to be applied to a 50 microfarad condenser, which is a capacitor, initially uncharged, to produce a steady current of 10 milliamperes. If the charging ceases after 10 seconds, calculate the voltage. So you're given a constant current of 10 milliamperes. and you know that the current across a capacitor can be written as CdV by dt. Um, you have CdV by dt equals to 10 milliamperes. You can integrate this, and you have the voltage, which would be so here we have, so here for the A part, the voltage is done for the final 10 seconds, but what you'll have to do is you will basically integrate. You have, so basically you have this equation, this one. After using this, CdV by dt is equal to 10 milliamperes. You integrate this from 0 to V volts and Vt volts for a time 0 to t, not 10 seconds. 10 seconds would be the final value. So you integrate it to 0 to Vt and the current to 0 to t seconds. You'll have 50 microfarads into V equals to the current 10 milliamperes into t. So that would be the voltage that would be linearly increasing with time. And when you want to find the final voltage, so this is basically the equation of the voltage from 0 to 10 seconds. Okay. And if you want to find the final voltage, you'll just put 10, t equals to 10, and you'll get 2000 volts. I hope that's clear. Here we have, so here it is integrated from 0 to 10 seconds. You just have to integrate it from 0 to t for finding the equation, and then put t equals to 10 seconds. Find for a general case, and then put the t equals to 10 seconds value. For the charge, you know that I is equal to dq by dt. I is a constant. You just have to integrate for the charge, and this is fairly straightforward. You just have to multiply 10 milliamperes into the time, which is 600 seconds, and you get 0.1 coulombs. The stored energy, we have the stored energy as half into CV square. You know the capacitance, and you know the final voltage. So the stored energy would be half into CV square, which is 100 joules. Any doubts in this? You can ask me. Right. So if there are no doubts, we'll move on to the last question of this tute, 16th question. This is you just have to plot the so you're given the voltage across. So these are two parts basically. One is given that this is a voltage across a capacitor, and it is a voltage across an inductor. So for the just a minute. So you have to basically plot the current profiles. You're given the voltage profiles, and you have to plot the current profiles. So you know that I across a capacitor is CdV by dt. We did this in the last question also, and the current across the inductor, we have the expression as V is equal to L di by dt, and we find that for calculating the current, we need to integrate the voltage for an inductor, and we need to differentiate the voltage for a capacitor. So you'll see that for the left hand side in the solution sheet, the left hand side graph, it is a differentiated version of the voltage that is given in the tute sheet, and for the right hand, for the inductor, you'll have a integrated version, and so the curvy nature of the graph. And these 25 milliamperes and these values would be decided by the capacitance and the values. I'm sure you can do this by yourself. You should try this once, and if you face any doubts, just message on the Teams. It would be better if you message on Teams, because many of you might have the same doubts, and they would get it cleared, and there would not be a lot of confusion among you. So yeah, that brings us to the end of the tute. Do you have any doubts? Just take time and think about all the questions that we've done. You'll have to try these yourself. Not very difficult for the first tute. So that's why we brushed like a little fast than usual. Just take your time and tell me if you have any doubts. I'll share this solution sheet also with you.
Sir,
Yes.
sir, for the quiz and the minor part, we have to write the answer